this is October-November 2021, paper 22. So we have to answer the first question in terms of prefixes. And tera is 10 raised to power 12. You know that. And minus 12 is actually pico, which will be small p with while mentioning that what is this prefix. So this is pico, right? Okay, then again, the question is about base units, underlining what are base units. So ampere is a base unit, and Newton, it's not meter is a base unit. And coulomb is actually Q equals to current multiplied by times. This is not a base unit, and Newton is again MA, not a base unit anymore. We have a formula, and we have percentage uncertainties. Let's look at the next part. He says calculate the percentage uncertainty. So how are we going to do that? We're going to see what formulas, which part of the formulas are actually involved in the calculation, up to what percentage. So D, since D is being squared, this will be multiplied by 2, and rest of them are all at standard values. I is involved, L is involved, V is also involved. So if we want to find out the total percentage uncertainty, then that would have been total percent uncertainty would be 6% because of this. So 6% plus 2% plus 2.5% and then plus 3.5%. So the total of this would become approximately, I think, exactly 15%. So there is a 15% error in the value of rho, which is mentioned at this point. He says absolute uncertainty. So what you simply have to do is that the formula was calculated as change in rho, or the absolute error in rho, divided by rho, multiplied by 100% would have given you the answer of 15%, which you just calculated. But since we are trying to find out the absolute uncertainty, then we have to multiply this 15% with the actual value. So that would be delta P equals to 0.15, 15% converted, multiplied by error in what? That is error in this, 4.1 power minus 7. So 4.1 into 10 to the power minus 7. Your answer comes out as 6 into 10 to the power minus 8. So this will be 6.0. Oh, sorry, errors are in one significant figure. So you're only going to write down 6 into 10 to the power minus 8 ohm meters. So then we have question number 3. Okay, so I've cut down question number 2 because that's not a part of your course anymore. We're only going to do question number 3, or we are going to start from question number 3. So define power, of course, that's rate of doing work, or work done divided by time taken for that process to actually take place. So that's your job to remember these definitions. The mass of the car is already given to you. There is an angle theta. Okay, fine. Then we have 25 meters of distance is being covered, and the resistive force is 440 that opposes the motion. So not only that there is a resistive force of 440 newtons, there is also the weight of the car, that is mg, and the component of weight that is responsible for pulling it downwards, or actually at least trying to push it backwards, is mg sine theta, because by geometry we know that if this is theta, then this will also be theta. Okay, so another backward component acting against the slope is mg sine theta, right? Okay, this is just a preemptive idea before we're moving on to the question. So he says for the movement of car from A to B, calculate change in kinetic energy. You see, it's mentioned in the question that it is moving at a constant velocity. If it is moving at a constant velocity, then even if I put in the value of half mv square, since the question is about change, the velocity is not changing. The change is 0. So the energy changing is 0 change in kinetic energy, or no gain in kinetic energy. It will maintain whatever kinetic energy it has. Calculate the work done against the total resistive forces. Now, since this is about total resistive forces, that is only the 440 newtons. So work done is equal to force into distance. So this is 440 multiplied by how long has it been moving, or how far, what distance has it covered till it experiences this much amount of work done. So that is 11,000 joules. Then it's he says that the movement of car in part B from A to B causes gravitational potential energy to increase by this amount. So calculate the increase in vertical height. So no problem. You see the car increases its height from this point and goes to this point. So there is a vertical change in height, which is what he's asking you. So no problem in this. We are going to simply apply the formula of mgh. So the energy is given to you as 4.8, right? So this will be 4.8 into 10 raised to power 4. This energy is being converted into height, right? So mg is already given to you as the 1700. So we just have to multiply this with the gravity, right? So this becomes 1700 multiplied by 9.81 multiplied by h, and 4.8 into 10 raised to power 4. Performing algebra will give you h equals to 2.88 meters, which will become 2.9 meters. Now he asks you to find out the calculate to the angle theta. So very easy to do that trigonometric in terms of trigonometry. So from point A to point B, it has covered a distance of 25 meters. And to get to point A to B, it has covered a vertical distance of 2.9 meters. So what will be this theta? Simple as that. So we're going to use the sine theta. So sine theta is equal to 2.9 divided by 25. And then you take sine inverse over there. So theta becomes 6.7 degrees. Then he says that the engine of the car B produces a power output of this much. Move the car along, calculate the time taken to move from A to B. See, to calculate time, we need the formula speed equals to distance over time, right? But we need speed over here. So how do we calculate speed from power? So power is equal to force into velocity. And how do we understand this formula? We say that if this is moving at a constant speed, or to maintain this constant speed against a resistive force of F, the engine must provide this much amount of power to do that. So power is already given to us, that is 1.7 into 10 raised to power 4 watts. But we're not familiar with the amount of force that is required. So to understand this, we go back to the diagram. We understand that this is moving at a constant velocity. That means that the forward force provided by the engine must be equal to this 440 and the mg sine theta. Only then the resultant, according to the idea of F equals to ma, the resultant becomes 0. That the pulling force of the engine minus all the drag components plus the mg sine theta equals to ma. This becomes 0 because the acceleration is 0, the constant velocity. So when it goes to over there, we realize that the force of engine is actually equal to the all resistive forces acting backwards. Only then this can happen, right? So over here, the force that is responsible, or the force that we're considering, is the backward force. Why backward force? Because we know that the backward force is equal to the engine force. The engine has to do, or has to provide at least bare minimum this much amount of force so that it can maintain a constant velocity while it's going up. So now we're going to add all the energies in this, all the forces in this. So we had 440 newtons in terms of drag and friction, plus the mg sine theta component of weight, which is also acting in the same direction. So this will be 1700 into 9.81 into sine of angle, that was 6.7 that you found in the previous part, 6.7. And when you perform algebra, of course, this whole is going to get added together and then divided with this one. So you find velocity as 7.12 meters per second. That means that the car is moving at a speed of 7.12 meters per second. The distance of path was 25 meters, so finding time is not a problem anymore. So we have the formula, speed is equal to distance over time. So let's swap the position of speed and time to see what the final answer is going to look like. So 7.12 equals to distance, that is 25 divided by t. So t comes out as 3.5 seconds. So your answer for the journey was 3.5 seconds. Moving on to question number 4. A velocity time graph is given for the child, right? For the remote control car that is being operated by the child. Okay, fine. The car horn continuously emit 925. So this is the standard frequency F0 from T0 to T6. The speed of the sound in air is 338. He says qualitatively, which means without calculations, predict what's going to happen. Any variation being experienced. So from T0 to T2. You see, in this region, the speed of the object is increasing, right? So if the car is moving away, and this is where it's written, begins to move in a straight line directly away from the child. So if the child is standing at this point and the car is standing at this point, the car is moving away then the frequency heard by the child is going to be less. So it is going to decrease, or you can say decreases, but in bracket it's understood that it decreases from 925 hertz to become something less than this. But when it starts to decelerate, when the object starts to slow down, its frequency, and let's imagine that when it immediately stops, the frequency will still be 925 hertz, heard by the person, heard by the student, heard by the child. So what's happening while it is slowing down? So first, its frequency became less as it was accelerating away, as it was moving at a constant speed away from the observer. The frequency was definitely less than 925. Now, as it comes to a stop, it becomes 925. So what is happening to the frequency? The frequency is increasing from previously decreasing to a certain value. Let's say it decreased from 925 to become, let's say, 800 hertz, for the sake of example, right? But now, when it slows down, it starts to increase from 800 back to 925. So over here, we will say that the frequency is increasing, and in bracket for your understanding, I'm writing down up to 925 hertz when it eventually stops. Okay, although it's not increasing more than 925, it is just increasing from the value it had when it started moving away. That's why it's increasing. Okay, then he says determine to 3 significant figures sound heard by the child that was emitted from t or at t equals to 3 seconds. So at t equals to 3 seconds, we realize that the speed of the object is around 12 meters per second. So since the object is moving away, the frequency that is heard is equal to the standard frequency f0 into speed of sound, which is 338, and then plus v0, which is of the object, which is 12. So I'm writing this as 12. And this f0 was 925. So the f heard frequency by the student, by the child, will be 893 hertz. So this is 893. Up to 2 significant figures, we will write down 890. Okay, so he says 3 significant figures, so we will leave it as 893. Okay, fine. So C part, he says determine the time taken for the sound emitted at time t equals to 4 to travel to the child. You see, up to t4, first we need to understand how far the object has gone away from the student or from the child. How far away is it? So to understand how far away is it, we need to find the distance. And in order to find the distance, we need to find the area under the velocity time graph. So first you mentioned that distance traveled by the object or distance traveled by the car is equal to area under the velocity time graph. You write down the statement so the examiner knows what you're doing, and then you're going to find out the the area under the graph up to 4 seconds. So we go back, and up to 4 seconds we realize that this is the graph that is going to look like. This is the total area that we have to calculate. You can either use the formula for trapezium, or you can use the formula, or you can use at least divide this into 2 parts. This is going to become a triangle, right? So what is the area? 1 over 2, base is 2, and height is 12. So this is the area of this part. Then we have the area of the square, which is this part, which will be base area, which is 4 to 2, so this becomes 2, and height, which is 12. So when you add all of them together, the total area or the total distance is found to be 36 meters. Now to find time, we have speed equals to distance over time. So speed is 338, distance is 36, time is what we need to find out. So time comes out as 0.11 seconds. So it takes 0.11 seconds for the time to come back from this toy car to the child. This question seems to be from stationary waves, right? Okay, a length of column of air is slowly raised out of water. And we are doing this so that a stationary wave can set up in the remaining column. The frequency is standard at 530, and the speed of sound is 340. It was already standard. It says describe a simple way the student, without requiring any additional equipment, can detect when a stationary wave of air column in the tube is going to be formed as it is being raised. You see, if a stationary wave is going to be formed, this end is actually a closed end, and a node should be formed at this point. And along the open end, there should be an antinode. Now, since you're using sound to set up stationary waves, you should hear a sound, right? But at antinode, what should be the sound heard? Should it be a loud sound or should it be a quiet sound? It will be a loud sound, because at antinode, even if you look at a stationary wave, at antinodes the particles are vibrating at maximum amplitude, and at nodes they're not moving at all. So node is quiet and antinode is loud sound. So he says without any additional equipment, so what the student must do, he must observe and hear a loud sound, as opposed to at other locations when the tube column was being raised. Okay, so determine the height of the top of the tube above the surface when the stationary wave first produced in the tube. Assume that an antinode is formed at the level at the top of the tube. Yes. So we have this tube. This is the water level, right? He says antinode is being formed at the top. Yes, we already know that the open ends make an antinode. So this is what the stationary wave is going to look like. So this is node, this is an antinode. This is actually lambda by 4, the length of tube which is given. So this is what he's going to ask us. What's the height? So we need to find the wavelength first, and once we find that, then we need to divide it by 4. So to find wavelength, we have V equals to F lambda, because this is quarter of a wave, right? If I want to make the full wave, then it would look something like this. This is from this point to this point, this is lambda by 2. So I hope we understand how to visualize this. So velocity was given to us as 340. Frequency is given to us as 530. And lambda is what we need to find out from the first step. So lambda comes out as part B is 0.64. So the wavelength is 0.64 meters, but the length of column that is available to us is actually representative of lambda by 4, wavelength by 4. So this is going to be divided by 4. So the wavelength comes out as lambda by 4, which is going to be 0.1, I think so. Yeah, 0.16 meters. Okay, fine. So when will this happen? This will be 0.16 meters out when the first stationary wave will be set up. This was the question. Okay. All right. Let's move on. All right. Determine the distance moved by the tube between the positions at which he first hears the sound and the secondary stationary wave being formed. You see, we have understood this in stationary wave chapter, that the possibility, what is the next possibility of the stationary wave that can be set up? If this is what the stationary wave looks like, an antinode at this point and a node at the closed end, this is lambda by 4 wavelength. And in the same amount of space, if you wanted to make another stationary wave, then the next possibility is going to look something like this. To understand how we have done this, and to understand how we have actually achieved this, you should go back and watch the lectures on stationary wave, right? That are uploaded on my channel as well. You can go back and check this. But this is what we're going to get, okay? So he says, determine the distance moved by the tube between the positions at which the first it is being heard and the next. So how much more do we need to move the tube to get the antinode again? How much more do we need to move the tube? We need to move the tube, or we need to provide an extra length of lambda by 2 at least. Or let's visualize it in this way. We understand that on the opening end, there should be an antinode. So let's say that this is that standard tube that we had already done, right? And how much extra space do we need to get the tube out of the water? This is the level of water previously, right? So how much more should we get it out so that we can hear the next possible sound, right? So let's go back to the diagram. Okay, so how long should I keep the tube out? How much more do the tube needs to get out so that we can hear the next possible? So the next possible case would have been something like this. An antinode at the top end, the quarter by wavelength, right? And the rest of the wavelength would have looked like lambda by 2. So how much more did you had to get it out? So you had to get it out at least lambda by 2 times more than previous, because lambda by 4 was already out. The length, of course, of the tube. So we need to get it lambda by, or at least half of the wavelength out, or half the wavelength of the tube should be taken out, removed from this situation. So the wavelength is going to look something like this, if that was set up. So the first antinode was observed at this location. So we have to keep on going forward. We have to keep on removing the tube from the water so that we can encounter the next antinode. So how much more did we have to go out? We had to go out at least lambda by 2. right? So this is going to become a 0.64 divided by 2, which is going to be 0.32. All right, question number 6. This is from electricity. There is an internal resistance. We have an EMF. Okay, fine. We have 0.8 amperes of current. There is a resistance of wire. Okay, good. He says calculate the charge passing through the cell in 7.5 minutes. No problem at all. We have I equals to Q by T. The current is 0.8. Q is not known. Time is 7.5 multiplied by 60. So Q comes out as 360 coulombs of charge. So 360 coulombs have passed through the wire or through the battery. Calculate the efficiency of the battery, what it provides to the wire X. So first we need to find out the power consumed by X, and then we need to find the power delivered by the battery to everyone. You see, battery is also powering the internal resistance, it's also powering the external resistive wire. So first, when we find both of them, we just simply have to divide them to find the efficiency. What the battery could have done when there was no internal resistance, for example, and what the battery has actually done for the external resistor when it is present. So in order to do that, we have the formula. We have two ways to do that. We have I square R, right? You could have applied I square R on both of them, but the issue is that we don't know the resistance, internal resistance, and we neither know the voltage consumed by the resistance. But we can do it in indirect way, is first find the voltage of the resistance wire, then subtract 0.48 from it, and then find out the voltage or the resistance of the internal resistance. But let's see how to do that. Do we even need it or not? So power consumed by the wire, at least at X, would be simply found by IV. So it is 0.80 amperes. And the resistance of the wire itself is 0.4 ohms. So this is 0.4 ohms. Very straightforward. No problems at all. But what about the power of the battery, right? So power of the battery is 0.48 volts being provided at 0.8 amperes. So that would have gone by 0.80 current multiplied by the voltage of the battery, irrespective who's using it and who's not. Okay. So we come down to, and then we multiply this with 100. Let's try to do that. Let's see what we get. So 0.448. Okay, so missed a step over here. You see, we had to use this formula, I square R over here. So this would be square, right? Because we don't have the voltage of the wire. I was using IV incorrectly. We don't have the voltage of the wire. We can find it, but it will add an extra step. We don't need it. So power consumed by the wire externally divided by the power provided by the battery at all costs or at all circumstances. So when you do that, you're going to get 67% as your answer. What you could have done alternatively is find the voltage consumed by the wire, which could have been 0.8 multiplied by 0.4, and then subtract 0.4 to find the voltage of the internal resistance. Then you could have used the formula V square over R, although the internal resistance matters are not required. But just for the sake of practice, you could have done that as well. Okay. All right. Then we have the next question. There are this many number of free electrons contained in the volume of wire X. We have no idea what is the volume of wire right now, but let's say that this is meter cube and this is the charge density N. The number density N of the free electrons. You see, to find out the volume, we need to first find out the volume of the wire. We go back and we see whether we have such data or not. Yes, we do have. So the length is 3 meters. The cross-section area is also given to us. So what are the dimensions of this wire? This is what it looks like. The cross-section area is given to you as A over here. And the length of the conductor is also given to you as L equals to 3 meters over here. So we can simply use cross-section area multiplied by length equals to volume. Where does this come from? For a cylinder, we know that the cross-section area is pi r square and the height is the length L, right? So we can find the volume of this conductor by multiplying cross-sectional area with length, which would be -7 equals to 3.9 into 10 raised to power -7 meter cube. Now, these are the total number of electrons existing in that wire. So if we want to find out the number density or the charge density, which is N, So that will be total number of electrons, which is 3.2 into 10 raised to the power 22 divided by the volume, that is 3.9 into 10 raised to the power minus 7. So that will be number of electrons divided by volume. So this comes out as 8.2 power 28 into 10 raised to the power 28 electrons per unit volume, per unit, per meter cube. You can say that if I had a box of 1 meter cube, 1 by 1 by 1, there will be this number of electrons inside this space if I made it from this conductor or material. The average speed of the drift speed of the electrons. So the formula is I equals NAQV, velocity, right? The current is 0.8. Charge density has been found by 8.2 into 10 raised to the power 28. The cross-section area is already known, 1.3 into 10 raised to the power minus 7. The standard charge is 1.6 power minus 19. We remember this. And now we can find the velocity. So velocity after algebra is going to come out as a 4.69 into 10 raised to the power minus 4 meters per second, which comes as 4.7 into 10 raised to the power minus 4. Now it says that a wire X has the same cross-section area as wire Y, X, and is made of same metal. Okay, wire Y is longer than wire X. So the resistance formula rho L over A, what has he said that is constant? He says that it is made out of same metal, so rho is not a part of the comparison. The cross-section area is same, so rho A is not a part of comparison. We are left with an increased length. So resistance is proportional to length. So if our wire Y has a longer length, then resistance of Y will be greater than resistance of X. Simple as that. He says is replaced with wire Y. Okay, assume that Y has the same temperature as X. Okay, state and explain whether the average speed of the free electrons in wire Y is greater than, the same as, or less than wire X. You see, since the resistance increases because the resistance of Y is greater than resistance of X, we observe that the resistance increases. If the resistance is increasing, then according to V equals to IR, if I take voltage divided by resistance equals to current, since the resistance is higher now, the current will decrease. And if the current is decreasing, then most definitely drift velocity will also decrease. Why? Because current is equal to NAQV. And if everything is constant, then current is proportional to drift velocity. If the current is decreasing, the drift velocity will also decrease. So that is the mathematical answer of this. And I've been speaking about the theoretical answer as well. This is what you can confirm from the marking scheme, and then you can write it in your own words how to write the answer. But I've explained the thought process of it. Question number 7, we have U. First, we discuss what is U. U is the atomic mass unit, and it has a value of 1.66 into 10 raised to the power minus 27 kg. This is given in the data booklet as well at the very beginning of the paper. So we believe that protons and neutrons, when they are inside the nucleus, this is their mass individually. But of course, we know from radioactivity and nuclear science that they are not same when they are out of the nucleus, when the nucleus has been broken apart. That is called mass defect. Anyways, that's a topic for another day. Okay, so we have a particle of mass 4U going this side and the remaining nucleus Q going towards the left side. If we go decay, it has zero momentum. It's not moving. The initial speed of the alpha particle is this. Okay, fine. Use the principle of conservation of momentum to explain whether the initial velocity of Q and alpha particle must be in opposite direction. You see, before the explosion happened, before they disintegrated, the momentum is zero, stationary at its own point, as mentioned in the question. So by this logic, if my alpha particle is moving towards this side, then multiplying mass into velocity, which is momentum, the velocity is on the right side, so the whole momentum becomes positive. Okay, fine. So according to my calculations, according to my understanding, this has to move in the left direction, so it can have a negative sign. So when we calculate its momentum, it possesses a negative sign, and when we add this negative momentum with this positive value of momentum, this positive added with the negative momentum should give me an answer of 0, because before the explosion, the momentum was 0. Okay, that is also the science of an explosion as well, by the way, that even if you only look at these two particles, what about a small explosive material that disintegrates in all directions? What about that one? So if you add all individual tiny momentums together, that will come to 0, because before it exploded, its momentum was 0, right? Okay, anyways, so by this idea, we can say that the momentum, we have to mention that the momentum before decay was 0. This is what you get. This is how you get the first mark. So after collision, and then you can phrase it in your own words, after the explosion, the momentum of alpha particle is positive. Hence, the momentum of Q should be, this should be negative, and negative momentum with the current reference, it should have a negative velocity, or it should be moving opposite to alpha. Okay, and I've explained the reason for that as well. You can use your own words to explain this. It says determine the initial speed of nucleus Q. No problem at all. You see, if this was 243 U and 4 U has been subtracted out of this, how many are remaining back in nucleus Q? So simply 243 minus 4 gives you 239 U. So nucleus Q has 239 U of mass. Now we have the velocity of alpha particle, we have the mass of alpha particle, and we know that both momentums are equal because they have to be in the opposite direction. So it goes something like this. That momentum of the alpha particle plus the momentum of the Q particle are equal to 0, which means one of them is actually has a negative sign. This is the theory that I just explained. So let's take this to the other side. So this means that the momentum of particle Q will be equal to the momentum of particle A, which is alpha. So based on this idea, let's try solving this. So momentum of Q, I need to know the mass. So that is 239 U multiplied by its velocity, I don't know, should be equal to the momentum of alpha particle, which has a mass of 4 U multiplied by its velocity, which I already know is 1.6 power 7. So this is 1.6 into 10 raised to power 7. So this velocity comes out as 2.67 power 5. So 2.67 into 10 raised to power 5. This is going to become 2.7 into 10 raised to power 5 up to 2 significant figures. Now, there is a problem, not the problem, but you can say an idea over here. You see, you could have replaced U as 1.66 into 10 raised to power minus 27 in this equation, but it will not serve any purpose because that is being multiplied over here and it is also being multiplied over here. So U gets cancelled out from both sides, although its value would have been this. So it's getting cancelled both sides. There is no point in dealing with this number, at least letting this value take part in this equation to make things easy for us. That's all. He says kinetic energy of the alpha particle. So no problem. Kinetic energy is half mv square. Now I need to put in the value of this atomic mass unit in the calculation of kinetic energy. So half in the 4 times mass of 1.66 of alpha particle into its velocity, which was 1.6 into 10 raised to power 7 whole square. When you find out this answer, let's say this is your answer. When you find it out, you have to divide this with the energy of an electron volt, which we have done in nuclear and radio physics, that 1 electron volt is actually equal to 1.6 into 10 raised to power minus 19 joules. But he's asking us in terms of mega electron volts. So no need to worry about it. Once you actually divide this with 1.6 into 10 raised to power minus 19, your answer comes out as 5, 3, and something with a few zeros with a few zeros, right? And that is going to be electron volts. So what you simply have to do is press the ENG button on your calculator, and this will automatically convert this for you like this: 5.3 into 10 raised to power 6 electron volts. So what is the 10 power 6? 10 power 6 is mega. So this becomes 5.3 mega electron volts. Simple as that. So this will become 5.3 mega electron volts. Okay. If it's becoming a problem, then let me show you on the calculator how it's going to be done. So I hope that we can see this on the calculator. Let's see that where those numbers exist. Let's clear this out. So what am I supposed to do? So 0.5 half mv square, I'm going to calculate it. 4 times 1.66 e power minus 27. Okay, fine. The velocity is 1.6 e7 with a square. Calculate this, you get this answer. Then this use fraction symbol, answer divided by the standard value, which was 1.6. So 1.6 power minus 19. Now when you press equals to, this is what you get. Okay. Now simply press the ENG button. You press the ENG button, it converts it to 5.3 power 6. As you can see that over here. Now what is power 6? Power 6 is mega. So no need to worry about this. Okay. All right. Question D is from alpha, beta, gamma, decay equation, so on and so forth. He says that N is shown, Z is shown, okay, fine. The graph shows a representation of nucleus P, which is given over here. So if I had to write down P, that would have been 95, and adding 148 with 95 would have given me the number that is represented here, 243. Okay, fine, let's go ahead. He says that a nucleus R has a nucleon number 242 and is an isotope of P. If this is an isotope of P, that means that the number of protons are going to remain the same. And it will exist on this line at least as a bare minimum, because I cannot change the number of protons for that particle. Now, to figure out whether it's going to be above it or below it, let's figure it out. So if it has 95 particles, right, 95 protons, and it has, let's say, the nucleus P is represented as 242 with the 95, then I can see that it has one less neutron. So it will be one step below this. Or if you want to do this the long way, then 242 minus 95 is going to give you 147, which is one less than 148. So your particle R is going to, P is going to exist at this. Is it P or R? This is R, This is going to be R. So this is where your R exists. Okay. Let's move ahead. He said the nuclear R then decays by beta and makes S. So no problem. So we have, was R. So R had 242, 95 decays to become S with a beta particle of 0 minus 1. So this will be still 242, but this will become 96. Okay. Now, one important distinction, since the proton number is 96, our particle is going to exist on this line at least as a bare minimum. Okay. Now let's make these particles. Okay. Let's do the calculations. So our proton number is 96, but what's the neutron number? So 242 minus 96. It gives you 146. 146. So let's find where is 146. So this is 146 line. And this is the 96 proton number. This line. So the common point of intersection lies at this location, which is very evident. This is the location, right? So let's clear this out and mark the point of that coordinate. So this is where that particle S is going to exist. All right. Let's go ahead. So he tells me state the name of the other lepton in addition to beta negative. And we know that when beta negative actually decays, we have an anti-neutrino as a part of the combination. So we will write down electron anti-neutrino. So basically this chapter is about memory. You have to memorize all of these outputs: hadron, hadron, meson, baron, leptons. It's all about memory. Okay. So this is what we just know from memory. That's it.